And things are getting exponentially more difficult now, just like quantum computing, right? We have learned the basics and we spend so much time, almost half of the semesters on the basics, is because I want you to really understand every algorithm qubit by qubit, okay? So there's nothing hand waving here, and you need to be very clear about what you are doing. So what is quantum teleportation, right? What is teleportation? My understanding is that in the movie, right, you suddenly will go from one place to another place in no time. And usually when we talk about teleportation, we talk about the teleportation of matter, which is impossible due to the general relativity, right? Because you cannot transfer energy of matter faster than the speed of light, right? Now here they call it quantum teleportation. What does it mean? We can discuss more later. But at the beginning, let's just think about teleporting a wave function from one place to another place very fast. Okay? But however, you will find that we cannot transmit information faster than the speed of light. So there's no problem there. But there is a very deep meaning about teleportation, which I will argue this is a very good name for it. So let's see what happened. So when we talk about teleportation, we have two parties, definitely, right? Because I want to send it from one place to another place. So I assume I have two people, two person. One is Bob, another is Alex. And they may be separated very far, one on the Earth, one on Mars. Okay? Now, Alex has a qubit. So here, when I draw this, is already a quantum circuit, right? And I assume the bottom is the MSB. I need this so that I know how to write my bracket notation or how to write my matrix, right? So Alex has one qubit. I call it psi. And we don't know what it is. Maybe she doesn't know neither. Okay? So we call it alpha 0 plus beta 1. Are you okay with this? Now you should be very familiar with the general expression of one qubit. Okay? Now Bob also has one qubit and it starts with 0. So here is the state of the qubit. So let's say it is implemented by electron spin. Okay? So how many electrons do we have here in this picture? 2 qubits. Alex has 1, Bob has 1. And the state of the electron Alex has is psi. The state of the electron Bob has is 0. Okay, if this is, let's say, spin up, then Bob has an electron having the spin pointing up. Alex has her electron having the spin in arbitrary direction that she doesn't know. That is a state he got maybe from measurement or not measurement, from another quantum algorithm or just anything, right? So now we form this as a whole system. So at this stage, right, I try to partition it. And you remember, for a quantum circuit, we go from left to right, in this class at least, right? And it is a time, right? You go from left to right, and then you do something. So at this stage, what is the total system, the wave function of the total system? How do you write the state of this total system? Tensor product, good. But what is that? Psi tensor. I know you are asking you something looks very simple, right? You already know that because you know this well in your midterm. I just heard from one of you. You learned this in Physics 161 today. Couple of days. Anyway, yeah. So it's good to review. Okay, and I can write it as what? Psi 0, right? And then what? And then you say I can write it as alpha 0 plus beta 1 tensor product 0, right? Up to here, is that clear? And you probably should know it very well if you was able to do question 2 in the midterm, the third part, right? If you know how to do the bracket notation, this is exactly this type of operation, right? So how do I write it? I want to expand it, become alpha 0, 0 plus beta 1, 0. Is that okay? Now, I'm saying that this is the states of the whole system, 2 electrons. Although these 2 electrons really separated very far, one is on Earth, one is on Mars. But it's still a whole system, right? I don't care other molecules, I don't care anything else. This is the system I have. And you trust me that it is very robust due to some reason, I don't know, what we were able to maintain there. So I consider it as a system, right? Then after this, we are going to apply a control NOT gate to it. Which one is the control qubit? MSB, right? Which one is the target qubit? So which electron is controlling another electron in some sense? Alex electron state is controlling the state of Bob, right? If you apply this gate, right? So after this state, right, what will it look like? Well, let's do a control NOT. I think some of you who are familiar with this already know how to do it by inspection. But what we're doing is just control NOT gate apply to psi and 0, right? And of course, some of you might want to write it as U exclusive OR if you want. It doesn't matter, just a symbol, right? Control NOT and U exclusive OR are just the same thing, right? It's just a symbol. Apply to alpha 0, 0 plus beta 1, 0. Based on the definition, right? Maybe I do one more step. U exclusive OR apply to 0, 0 plus beta U exclusive OR apply to 1, 0. Is this okay? If no, step back. U is a matrix. This is a vector. Alpha, beta are just scalar. So I just take alpha, beta to the front. It's just a number. And then I apply, due to this distribution law, apply this matrix to the first vector plus the matrix to the second vector. And what is the definition of control NOT gate? If the control qubit is 0, do nothing. If the control qubit is 1, apply NOT gate to the second qubit, right? So we don't have anything change, right? Or you look at table, right? So the first one is what? Alpha, still alpha, 0, 0. How about the second one? Second term. 1, 1. Thank you. Because the control qubit is 1, we apply NOT gate to the second qubit, so it becomes 1, 1. And why do we do this? Obviously, we try to do an entangled state, right? And that makes sense, because if I want to do some quantum teleportation, I better to have some build some relationship between 2 electrons, right? In that sense, right? If they are not entangled, how can I teleport some information from one electron to another electron? Anyone notice the problem of this setup? Practically, what is the problem practically? You need to have a control NOT gate that apply to 2 electrons. One is on Earth and another is on Mars, right? So that is like a super big control. Of course, control NOT gate is not about the size. It's about you apply a Hamiltonian. And if you have learned about how to implement in hardware, for example, trap ion, you actually shine a laser beam, a laser beam to them, and then they need to interact with each other. How can you let 2 electrons separated so far to have a control NOT operation? It's difficult, right? So this is a simplified version. Okay, and we take it for granted that we are able to build this entanglement. And later we have a more complicated version which will be practical for us to build the control knot operation. But our goal is not to do control knot. Our goal is to build the entangled state. So later we'll show how to build an entangled state. Okay, but let's take it for granted for now, right? So now I'm going to say this is step 1. Okay, so the step 1 is that Alex and Bob are separated. We apply a control knot operation, so the two electrons will get entangled. Okay, and then we have an entangled state. Any questions? If no, then I would like to go to the second step. So this is just descriptive. So Alex is going, so just a reminder right now, the state, total system, is in this state. Alpha 00 plus beta 11. Okay? And I want to remind you, this is actually, the first 0 belongs to Alex. The second 0 belongs to Bob, right? The first one belongs to Alex. The second one belongs to Bob. We already know that. I just remind you by spelling it out. Yeah. No, they are not sending each other. So just we assume at the beginning, Alex is on Earth has a 1 electron, and then Bob on Mars has another electron. And we were able to do entanglement between these 2 electrons, right? You take it for granted, right? And then these 2 electrons form a whole system. Now they are entangled. They are not sending anything to each other. But later we will send something when we don't use the control NOT gate. Okay, so what are we going to do now? So Alex is going to do a measurement. But, of course, she can only measure her qubit, right? Because Bob's skill is on Mars. She cannot measure. So she's going to measure her qubit, but using plus-minus basis. What does it mean? When he measures, her electron will collapse to plus or minus, okay, instead of 0 or 1. She can choose how to do measurement. And I told you earlier, maybe you forgot, for example, 0-1 state is maybe like I have the magnetic field in the z direction. I just measure whether it's spin up or spin down. When she chose to measure in plus-minus basis, she will set the magnetic field in the x direction. Then she will try to measure whether spin collapse to left or right. Okay? Don't need to exactly understand what is the meaning of this physical implementation, but what we need to know is that when you choose to measure in this basis, we better to do transformation so we can see the outcome. Now the state is what? Alpha 00 plus beta 11. So what I'm going to do is going to substitute this. So I think, did I do okay, that is correct. Okay, so as I told you, right, this is alpha 0 Alex, 0 Bob, plus beta 1 Alex. 1 Alex, 1 Bob, right? But because 0 equals to 1 over square root plus minus. And 1, of course, they all belong to Alex, right? Equals to 1 over square root plus minus. Again, they belong to Alex instead of Bob, so it should be A. Do you remember this? We have done some similar transformation before, but this is given. Okay? The plus state, 0 state is a linear combination of plus and minus, And 1 is a linear combination of plus minus also, right? Plus minus are the eigenvector of sigma x. 0 and 1 are the eigenvector of sigma z. And we have done some transformation even in the midterm at the end. We have the ask you for transform matrix from the eigenbasis of x to eigenbasis of z, sigma z, right? Okay, so I just want to express it differently, right? So 0, 0, 0, a becomes 1 over square root 2 plus a plus minus a, and then the whole thing 0. And then the second part, beta, again 1 over square root 2 plus a minus a, and then the whole thing 1. Do you see what I'm doing? 0, 0, 1, 1, I write it explicitly 0, 0, 1, 1. Alex 0 is just equal to plus minus, right? So I substitute this 0 by this part. I still copy Bob's. And then here, Alex 1, I substitute with this plus minus minus. Is that okay? Any questions? And then I'm going to group the term because I'm measuring in plus minus basis. So I want to make Alex qubit represent in plus and also minus. And then I know how it will collapse, right? So if I group the term, I want to look at plus first. So basically, I will have 1 over square root 2. I just take it out, the whole thing, alpha. And then I have this plus a, 0b plus 1b plus beta minus a plus 0b minus 1b. Right? I'm doing it a little bit fast, but let's just take a look. What I'm doing is just expand the terms. So I have plus a times 0b, right? I also have plus a times 1b, right? Yeah, so obviously I'm doing it wrong. So I should actually do it step by step. Sorry for that. So I did it wrong. Let's take a look again. I have plus a times 0b, right? And this is alpha. And then plus a times 1b, and this is beta. Can you follow? Okay, let me do it. Let me expand it again. So every, oh, what did I do? They're all gone? I don't know what I pressed and they are all gone. So let me write one more time, sorry. I'm going to redo it, right? So now, at this stage, right, what is that? We have alpha 0, 0 plus beta 1, 1, correct? And let me continue to write it as, I just continue to write it, okay? 0a, 0b plus beta 1a, 1b, right? Bob and Alex, right? And then again, I give you 0a equals to 1 over square root 2 plus minus. I'm okay, let me still call it a. And then 1a equals to 1 over square root 2 plus b minus minus. Still okay up to now? Now I'm going to substitute, right? Therefore, because of typo, thank you. It's completely wrong. Should be A. It's Alex. Good point. Okay? Because of this, so now, still the same. It is this, right? Equals to alpha 1 over square root 2. So I want to stop writing the A because it is troublesome for me. So I A, B, right? But you know that the first one is A, second one is B. Plus beta 1 over square root 2 plus my, and this is a typo, right? No one pick it up. Is this step okay? I'm just doing alpha. 0a becomes half 1 over square root 2 plus minus. And then 0b is 0b. Beta 1a is 1 over square root 2 plus minus minus. And then 1 is 1 for b.
I think outside it has to be inside the
Inside where? You think it's good? What do you think? You inside where? Okay, alpha is multiplied to 0a and 0b, right? So this whole thing is 0a.
oh,
Yeah, okay, good. Now, so what I'm going to do is just continue, but instead of last time, right, I jumped too fast. I am going to do it term by term. So I have 1 over square root 2 alpha plus 0 plus 1 over square root 2 alpha minus 0 plus beta, or 1 over square root 2 beta plus 1 minus 1 over square root 2 beta minus 1. Do you see that? I have 4 terms because this is plus minus times 0 plus minus times 1, right? So I have plus 0, which has alpha, minus 0, also alpha, beta with plus 1, beta plus 1, negative beta times negative 1. Is that okay? Right, you just go through the math. And now I'm going to group them. I want to group the plus term together. So this is equal to 1 over square root 2. I can group the factorize the plus, right? So this become plus. And then alpha 0 plus beta 1. That was my mistake last time. Because here, I take alpha is just a number I put inside. So here I have alpha, I have plus, and then alpha 0. Here I also have plus, beta 1. Do you see that? Or just opposite, reverse. This multiply this plus this multiply this equal this term plus this term. Okay? Then how about the other one? The other is the same. I want to group the minus term. Minus, what do I have? Someone tell me. Let's say again. I take the minus. Is it? Say again. What's 0? Thank you. Alpha 0 minus beta. No, I have typo. Alpha 0 minus beta 1. Thank you. Right? Because for this term, I take out the negative to here. Right? This is the state. I just need to keep the relative position of the state. But for number, scalar, I can put anywhere. Right? Again, because this vector, this is just a number. So negative is here. Then I have alpha 0. Negative is here. Then I have negative beta 1. Do you see that? Now this is very interesting. How many qubits do we have here again? 2 qubits, right? Still 2 qubits, although you have so many terms. But which part belongs to Alex? Which part belongs to Bob, based on tensor product? Obviously, the first one belongs to Alex. The second one belongs to Bob, right? If you trace the index carefully. Right? This 0, 0, 0, 1 all belongs to Bob. And this belongs to Alex, right? So that's why now Alex will say, Alex, so I need to say step 2. Alex will perform a measurement. It measures her qubit 8 in plus minus basis. Okay, with this so much math is just because I want to transform it to plus minus basis for Alex. So these are orthogonal bases. They are the eigenvector of sigma x. When you do measurement, what happened? Collapse. Very good. So it will collapse. What will it give you? Yeah. So it has some chance. Here actually 50% chance. You may get plus. Okay? So Alex will get plus. She measure. Oh, it's spinning to the left, for example. And then what? If it get plus, then it means Bob gets what? Huh? 1 over square root 2 alpha 0, thank you, plus beta 1. Correct? Because once it collapses to first term, right? So Bob's state is already here. Make sense? And what is this state? Sorry, this is exactly the state on Alex qubit. But when Alex measured, does Bob know that Alex has done the measurement? No, right? I didn't know that you were so what? You are not busy now. I thought you were very busy and you did the measurement. I thought you were sleeping, right? How can Bob knows that his state has collapsed to psi? He has no way, unless Alex is very trustable, and then what she's going to do is, if it get plus, it's going to call Bob, no matter what method. Use satellites or fiber optics, or just take the Elon Musk SpaceX to Mars to tell him, right? It won't be faster than the speed of light, right? Via classical communication. That he needs to do nothing. Doing nothing means what? Apply what gate to his qubit? Apply IB. Yeah? Yeah.
Just a minor point, we need to normalize Bob's qubit.
Normalize Bob's qubit, you have to. Thank you. Thank you. That's a good point. Thank you. So, very good. So he said a very good thing. I still keeps 1 over square root 2, which is not psi, right? But because after your measurement, it will need to get normalized. Very good, yeah. And this is not minor, right? So important. So do you see this? Alex did the measurement. This time she got plus. This process has not finished. She called Bob, said, hey, I got plus. Then Bob knows that. Great. Then now my qubit has your state. Even Alex doesn't know what state she had. Alpha 0 plus 1. Bob also doesn't know what state he got, which is alpha 0 plus 1. But we have successfully transformed the quantum states of the electron on Earth to the electron on Mars. Still no time, like teleportation. But in terms of information transmission, it's still slower than speed of light, because you always need to make the classical call so that we are sure that it is transferred there. So Bob will not receive information from Earth faster than the speed of light. That's first thing. Make sense? Second thing, is this a cloning? Your question? Yeah. It will, because when she did the measurement, she get plus, then she's going to call Bob, say, I got plus. She needs to tell Bob that she got plus. Because if she got minus, there's another thing Bob needs to do. There's nothing about channel security. Think about, through this process, I transfer a quantum state, which I don't know, to another qubit. How do you do that? Right? I teleport the state to there. I'm not copying though. Why I'm not copying? No cloning. Why there's no cloning? Because the original bit becomes plus now. 1 over square root to 0 plus 1 instead of alpha 0 plus beta 1. So no cloning. Alex need to destroy her qubit in order for Bob to get the state. And then why this is teleportation? I have some thoughts, maybe I'm wrong, but think about elementary particle. You cannot distinguish this electron and that electron. So if I copy the state of this electron to that electron, it is like teleportation of teleporting this electron to Mars, right, in no time. And I can even think that if I have a very sophisticated algorithm, if myself is form of 10 to the power 30 atom or 25 atom, and all this elementary particle has a state, right? I just do a correct algorithm, I can teleport my states, every state, including my mind, if you believe everything is quantum mechanics, to someone on Mars, which has an exact copy, exact atomic number as me. But once you teleport there, in principle, you will just form myself, because all this, the bonding in my body, my spirit, right? If we only believe in science, they will just copy to there. And then the one on Earth will just collapse, right? Because all my state will just collapse and my body will just disassemble or whatever. But isn't that, looks like a quantum teleportation, if that works well in that sense, right? If I can teleport one electron, I can teleport water molecule. That should be no problem, right? If everything works out with this quantum circuit. I still not transfer things very fast, much faster than the speed of light, but I'm teleporting in that sense, right? So I think this is a good name about quantum teleportation. But we are not transferring matter, we're transferring the state. But if you look at elementary particle, I feel that it's just like transferring myself from one place to another place. I don't need to go through this difficult journey of like 180 days to Mars and eat those space food, right? I just go there and enjoy my life. I don't know if that makes sense, right? Okay, so this is step 2. Oh, and then, my God, I thought that I have a lot of space. Yeah. Because the Bob still did not get the information that Alex already measured. You need to wait for Alex to call her. So that he knows that there is something. So I would do something more practical, right? For example, let's say if, right, if I have an example in the book. Let's say you're doing some gold mining, rare element mining in Mars, and then now Alex, oh my God, the Earth just discovered a big mining whatever miles, and then Alex can call Bob if you can transfer the speed fast, or opposite. If Bob try to teleport to the Earth, he can call. Let's say Alex is on Mars and Bob is on Earth, and then he will just call Alex, say, "Hey, sell the stock because we found a lot of gold here. Gold is going to be so super cheap, right?" So he can do, if he can transfer this information faster than the speed of light, they are going to earn a lot of money by doing this, right? Because all other people need to wait for telecommunication to say, oh, we discussed a gold mine in Mars, so gold is not going to be expensive anymore. But no, but you still need to wait until Alex on Mars to call you that I already done the measurement, you got my state already, something like that. You see what I mean? Yeah. So no useful information. Yeah. Although the process you feel that is instantaneously, but this I cannot explain philosophically, but no useful information. So I run into a problem because I thought I have one more slide left, but I call this step A. Now go to previous page. And then I'm going to say step 2B, see previous page. Huh? So I'm going to copy this one, step 2A, next slide. Okay, and this is step 2B, come back. So what if Alex gets minus? Again, there's no guarantee, right? She can get plus or she can get minus, correct? So what is Bob's state? Then Bob has 1 over, again normalize it, so has alpha 0 minus beta 1. Almost there. You almost successfully quantum teleport your state, right? But no problem. Right? So Alex again is going to call Bob and say, I got minus. Then what will Bob do? Then Bob will apply a NOT gate. No, C gate, phase shift gate. This is C gate. To his qubit. And what is a Z gate? 1, 0, 0, negative 1 is a phase shift gate. What does it do to the 0 qubit? For 0, I mean, nothing. What does it do to 1? Not flipping, add negative 1. Right? Then Z alpha 0 minus beta 1 equals to alpha Z 0 minus beta Z1, which is equal to alpha 0 plus beta 1, which is equal to psi. Okay, so they still don't know what they have. But Bob needs that. I don't care what I have. I just apply a Z gate to my qubit. Then I will get the state that Alex had. Because Alex was alpha 0 plus 1, and Bob get alpha 0 minus beta 1 instead of plus. Now he applied the phase shift gates. Then he got alpha 0 plus beta 1. Yeah. No. No. Yes. So after measurement, Alex need to call Bob through classical channel. Alex got plus, no matter what, if Alex got plus, he called him. I got plus. Bob said, let me just apply identity gates. Means do nothing. If she got minus, she still call him. But now he knows that he needs to apply a Z gate. Then he will get alpha 0 plus beta 1. Okay, so one classical call to finish this quantum teleportation process, a simplified version. Is that okay? Okay, so go back to think about it, right? So same, Alex qubit got destroys because she got negative now, right? But now the problem is we really cannot afford this super large control NOT gate. So what can we do? Then we need something more complicated. So we are going to replace step 1 by something. Step 1 is what? Entanglement formation, right? Let me put the by here. Right? By a new circuit. And look at this. This is complicated. I have a 9 here, a 9 here, a 9 here. I need 3 qubits. Still MSB is at the bottom. The bottom one is still Alex qubit, but the top one is still Bob, right? And then I add a new qubit, just call it BB, okay? Just a label. So again, we start with 0, 0, and psi, okay? So we just go back to very beginning, okay? Now and the interesting thing is now we have this 2 qubit at the beginning in Bob. In Bob's laboratory. So in this sense, maybe they are both on Earth, on Mars, okay? So Alex resides on Earth with 1 electron. Bob has 2 electrons on Mars, right? It's easy to get 2 electrons on Mars. And then what do? They are going to do this. Bob is going to apply a Hadamard gate to BB, and then a control NOT gate to both of them. Do you know what is the purpose of this? Bell state or entanglement, right? We try to do entanglement. So let me just draw a line here. So what is the total state of this system, right? It's going to be psi A because MSB is at the bottom, 0 BB, right? And then 0 B. That was the initial state, correct? And then we're going to apply this. After this, after you apply, what should I draw it? Maybe this can confuse you. Let me do not draw this. Yeah. So now I'm going to apply 2 gates. The first gate is the Hadamard gate. Let me make it longer. How do you apply the Hadamard gate? Only to BB. Then what gates do you apply to the Alex and Bob? Thank you. Correct? And that is tensor product. And after that, we apply a C0 gate. So I'm going to also apply a control NOT. What do I do to Alex qubit? Or instead of C0 gate, let's just write U exclusive for. This is only 2 qubit, right? C0. What do I do for the MSB? Still I. So basically apply these 2 things, right? And then try to get something. I want to see the output, right? So we break it down. So if you do this, you will see when you apply IHI to psi 0, 0, it means what? It means you apply psi is not changed, apply H to 0, and then the last qubit also doesn't change, right? So I may be a little bit messy, but I think this is a good practice to make sure that you understand things well. Again, we have 3 qubit. This is tensor products. This is tensor products. This I only apply to this one. This only apply to this one. This only apply to this one. If I want to make it very clear, or you really want that, this can be IA. This is BB, HBB. This is IB. And this is A. This is BB. This is B. Make sense? So that's why this is still A. This is BB, BB, and then B. Correct? Any questions? Right, I have 3 gates. Each gate applied to each corresponding qubit. And what is the result of this one? Well, when you apply Hadamard gate to it, you get 1 over square root 0 plus 1. Correct? And of course, these two are the BB state, right? BB, BB. Okay? And after that, you apply the control NOT gate to it. And I'm going to write this as 0, 0 plus 1, 1, 1, 0. Right? I just combine this 0, 0 and 1, 0 together. Make sense? What do you get when you apply control NOT gates? This is for this 2 qubit, right? When you apply to this, what do you get? 0, 0 and 1, 1. So this one gives us psi 1 over square root 2, 0, 0 and 1, 1. So this is an entanglement. So basically the whole process here, if I call it 1A, right? If I call this 1A, is just to create entanglement. Between B and BB. And this is just standard entanglement process. I write it in a very complicated way by involving Alex qubit, but you see that Alex qubit always receives identity. I could have just applied Hadamard gate and log gate to this 0, 0 state. Very simple, but I deliberately show everything. Questions? Is this clear? So at this stage, Alex is not affected. Of course, it's Bob playing with his two electrons on Mars. My qubit, my electron is still here. Nothing is affecting me, right? So Alex is still psi, but Bob got this entanglement state. So in some textbook, they will just say create an entanglement, right? It did not really go through, looks like a big algorithm, but just create an entanglement on Bob's lab. So this is step 1A. Now then the second step is like this. I continue to extend this 9. I really should draw it better. Now that's what we need to do. The second step is physical step. Bob is going to send BB to Alex's lab. So now they are in the same lab. So do you see that on Mars, Bob entangled 2 qubit, then he need to rent a SpaceX or whatever, send that electron back to Earth. And in this process, you need to make sure these 2 qubits are still entangled. Now, thinking about electron will be difficult, but if thinking about optical fibers or whatever, that's no problem. So think about you build a really long fiber, or you use some way to do satellite communication using photon, you probably can send one of the qubit to Earth, and while they are still entangled, right? And I think there has been experiment to do this type of experiment between Earth and the satellites. I think it was from China, and then they let the satellite fly to Europe and then communicate with a station in Europe. They successfully do this quantum communication, right? But anyway, we assume doing this is much easier than building a CNOT gate that can cover Earth and Mars. Okay, so after Bob done the entanglement, he sent the qubit to Alex. So I spent so much time on this, but actually you can summarize as Bob entangled two electrons and send one of the electrons to Alex. That's what I've been talking so far. Okay, so you feel that the important thing is that you cannot do teleportation just because you want it. You need to prepare for it. So in order to do teleportation, I need to entangle my electron and send it to Alex and wait until a day suddenly Alex wants to teleport something to me. Then she's going to use that electron. And we will see how you use it. So this is step 1B. So at this stage, right, let me repeat. This is Bob. And this is BB. And this is Alex. This is still MSB, but now, right, everything is in Alex's lab. Is that okay? Right? Now, and then what will happen? Then Alex is going to apply a gate to here. And this is the CNOT gate. And after that, she's going to do a measurement. Okay, so here can have a very long time lapse, right? Because Bob prepared the entangle stuff as entangled electrons sent to Alex, and they just wait until there's a war or whatever. I'm going to teleport something to you. Can you imagine, like they're the same country, right? And then they just building this channel. They are not sending anything yet. Until a day, suddenly Alex decided that she want to do the measurement, then she will do something. So then what will she do? She will do a control NOT gate. Then let's look at it, how it works, right? So after control NOT, what would it look like? So if you look at the previous one, right? If you look at the state, it originally was psi. Originally, you have psi 1 over square root 2, 0, 0 plus 1, 1, right? I'm just copying this one. Is that okay? That was after entanglement. And even you transfer the electron to Alex, you still have this state, which becomes alpha 0 plus beta 1, the whole thing times 1 over square root 2, 1, 0, 0 plus 1, 1. And all we need to do is just expand it. Then what do you get? You get 4 terms, right? 1 over square root 2, alpha 0, 0, 0, plus alpha 0, 1, 1, plus beta 1, 0, 0, plus beta 1, 1, 1. Do you see that? Because I just expanded alpha 0, 0, 0, alpha 0, 1, 1, beta 1, 0, 0, beta 1, 1, 1. I get 4 terms. This is just the states after Bob has done the entanglement. Well, I have not done anything yet. Maybe I should remove this one so you won't confuse you. Okay, so we have this term, right? Let me double check. Okay. Then, now, so Alex, apply C0, right? Then the state, let me write it again, 1 over square root 2, alpha 0, 0, plus alpha 011 plus beta 110 plus beta 101. But what is this control now? Which one is the control qubit by Alex? Huh? MSB, Alex, right? Which one is the target qubit? The middle one, BB, right? So let me remind you, A is control, B is target. So after apply C naught, what happened to the first term? Alpha 000. Huh? What happened to alpha 000? Nothing. Because the control qubit is 0, target qubit, then do nothing. Okay? How about for this term, second term? 011. What happened? Also nothing because control qubit is 0, right? How about 110? Becomes what? 10 what? Someone say 101, someone say 100. Based on this diagram, what should that be? So it was 110. 100. Because the target qubit is BB. It has nothing to do with Bob's qubit, right? Alice was doing control not in her lab, right? It's not affecting Bob's qubit, right? So how about the last one? Becomes 111. Wasn't it 111 before? So thank you. So I copied the wrong line. I actually copied the result. So you're right. Then I think I got it wrong also here. 100, right? So sorry, I copied the result instead. So this should be 100. So I was wrong, right? So here was beta. What's that? Beta 100, beta 111. So it should be beta 100, beta 111. After control naught, it should be beta 110 and beta 101. Is that okay? Right? So you understand that is what it does, right? Then what will Alice do? She will do a measurement on which qubit? Second qubit, right? The BB qubit, right? This is given. So Alex, measure qubit BB. What will happen? If she measure the middle qubit, what will happen to the qubit? Collapse. It will and also I need to say on the 0-1 basis this time. So it will collapse to what? We don't 0. If she gets 0, the wave function becomes what? We are talking about the middle qubit becomes 0, right? So the wave function becomes alpha 000 plus beta 101. Because this is 1 in the middle. These are all gone. Right? You measure partial measurement, right? Now, although I have 0 here, but just happened that I arrange it in the middle. It is a tensor product which I can factor out, right? But mathematically difficult to see it, but you can think about how about I just rearrange it, put it as the MSB or LSB. Basically, this is the same state. So I can just say that if I, don't worry, this is just like, this is A, BB, B, A, BB, B, right? It's just the same as alpha 0A, 0B plus beta 1A, 1B. Are you okay? I just take away BB because I can factorize it. Make sense? Okay? But what is this? Look at this. When we do the entanglement in this simplified version, our goal is to get alpha 0, 0 plus beta 1, 1. And we do get alpha 0, 0 plus beta 1, 1. Right? So what will Alex do? She will call Bob again, but actually this is the first time she will call in this algorithm, and say, I got 0. So Bob, what will Bob do? Nothing. Good. Which means apply IB, because they already get the entangled state. So what happened again? Bob original has a 2 electron entangled on Mars, and then he sent 1 electron to Alex. Alex did the control NOT gate and measurement, and this time she got 0. Then she just called Bob, say, I got 0. Oh, great. Then our 2 qubits already entangled in this state. So we can continue. So can continue. Step 2 for teleportation. Right? But what if Alex get 1? Then what would it collapse to? Alpha 0, 1, 1 plus beta 1, 1, 0. Everyone can follow him? Because the middle is 1, right? And again, the middle is 1, both is 1. I can factorize it out, right? Again, difficult to see in this arrangement, but I can always swap them now, right? Because it doesn't matter how I label them, right? So that means now I have alpha 0, 1 plus beta 1, 0. Again, this is A, this is B, this is A, this is B. Is this what we want? We want alpha 0, 0 plus beta 1, 1, right? Then they won't say I give up. What would they do? Can you guess? X. Great. So she will call Bob again. He said, oh, I'm sorry, I need to do more because I got 1. And Bob, okay. It will just apply X gate to his qubit. He applied X gate to his qubit means that Alex does nothing, right? Alex applied identity gate. So you are just applying I tensor product X to alpha 0, 1 plus beta 1, 0, right? So here I deliberately write the tensor product, right? I don't have to. Here I did not, right? But I only apply to the first qubit, X apply to the second qubit. So this gives me what? Alpha 0, 0 plus beta 1, 1. So again, done. Continue, step 2. Right. So maybe I should have taught this first, but it doesn't matter. The point is you realize that I need to get them entangled in order to do quantum teleportation. And how many classical core do I need? Very good, 2. Summary. I need 2 classical core. The first core is to establish the entanglement between those 2 qubits. And I need 3 qubit also for this whole process. And also I need 1 transportation of the qubit. I need to physically move 1 qubit to Alex. Although that is a dummy qubit, ancillary qubit, right? We don't use it. And eventually, I'm able to teleport the state to Mars, but my state got destroyed. Okay, so you can go back, but I can just say one more time what we do. Bob has 2 qubits on Mars. Alex has 1 qubit on Earth. Bob will first do an entanglement on his 2 qubit. Then he will physically send a qubit, which is slower than the speed of light, to me. But this process is okay. You don't consider as the teleportation. It's just a preparation. He need to send it, right? Like establishing an office in Mars. I want to prepare for teleportation one day. I don't know when, but Bob will entangle and send 1 qubit to me. So Alex has 2 qubits. Bob has 1 qubit. His qubit is entangled to 1 qubit in the lab of Alex. When Alex wants to do quantum teleportation, she will do a control NOT gate and then measure the ancillary qubit, the middle qubit. Then she is going to call Bob, say that I got plus. Bob does nothing. They say we are ready to do teleportation. Not plus, sorry, got 1. But if got 0. And if she got 1, Bob need to apply NOT gate to his qubit. Then they are ready to do quantum teleportation. So at that stage, then you will go back to this quantum teleportation. Alex will measure in plus state for her qubit, and then call Bob. If she get plus, Bob will say, okay, you teleported the state to me successfully. If she got minus, Bob will apply the Z gate, and we also quantum teleported successfully the state to it. Okay, so to study this topic, right, one is the math, second is think about this whole process. Okay, try to draw some pictures. Good. So, yeah.
In the previous step, right, when you entangle the Bob qubit and the BB qubit, so that 2 qubits are entangled.
Yeah, entangled, yes.
So when you measure 1 qubit, then
Yeah.
the other will be collapsed.
Correct.
So how come the BB qubit is collapsed because the measurement, right?
Yeah.
But the Bob qubit is still in the entangled state.
It is something a little bit like entanglement swapping. Now, actually, Bob's qubit entangled with Alex's qubit through another mean. Do you see that? Yeah, you're right. So originally, the second qubit, we can look at this. This is a good question. Like, this is the original state. You see, second qubit is entangled with the third qubit because 0, 0, 1, 1, 0, 0, 1, 1. Whenever it is 0, 0 for B, 0 for BB, it is 0 for B. When it is 1 for BB, it's 1 for B also, right? But after this measurement, you look at it, now you lose the entanglement between B and BB. But now, Alex, A and B become entangled, 0, 0, 1, 1, 0, or even opposite, also entangled, right? This is anti-correlated. When you are 0, I'm 1, and you are 1, I'm 0. So do you see that when you do the measurement, you destroy the entanglement between BB and B, but then you establish entanglement between A and B. Yeah. But that's math, okay. So that's the math. It's good to understand it. I mean, you can learn a lot by going this one again and again. Now here I want to talk about the IBM Qiskit just to do some more explanation, because later you need to implement this in your class homework. So we have 3 qubits here, Q1, Q2, Q3, right? Again, the bottom is MSB, right? By convention. And this is LSB. We also have C4. It means I have 4 classical registers. To store your measurement result. Is this okay? Although I have 3 qubits, but I deliberately make 4 classical registers. That's it, I just deliberated, okay? So I want to show a few things. If I call this as A, this as B, right? And then C, D, E. Then if I look at a classical register, I have 4 of them, right? I have the first, second, first and 0 because we're counting from 0 to 1 for the register. This is classical. And this is, of course, is the MSB. We also have MSB and LSB for classical register, right? So at A, what are the value of them? The register is there. Whether you run quantum circle or not, it is there. So at A is the initialization. By default, they all got 0. So if you try to plot it, you get 0 at state A. Is this okay? This clear? How about at state B? What will be the value of the register? I apply a NOT gate to number 2. Someone say 0, 1, 0, 0, right? But at state 2, did I do any measurement? 9, 2, here. Have I done any measurement? No, yeah, you apply the gate to QB, you did not measure, it doesn't give me any result. Actually, nothing happened. Make sense? So at this part, if you look at the register, you will get 0, 0, 0, 0. Because there's no measurement. B. At B, there's no measurement yet, right? The time go from left to right. You apply a quantum gate to Q2. But you have not measured yet. You did not store anything to the register. And then at C, you did a measurement. The measurement say store this to 2. 2 means the second qubit, second classical register. So at C, it becomes 0, 1, 0, 0. Because you measure, now you already have this is state 1. And you measure it's always 1. And you store to the second register. So you have 1 here. Ali, make sense? Looks like you don't agree with me for B, right? For B, I have not done any measurement. Okay? You use the gate, you change the qubit, but you did not do the measurement. You still have the classical register. It's just that the classical register is your brain. If you did not look at it, how can your brain's information change? That's the point, right? Make sense, everyone? And then now I look at it and measure it, right? And I say save to 2, right? How about here? After at D, what do I get in this register? D, I do one more measurement, but I say save it to register 3. I say save it to register 3. Yeah. 1. Is it 1000 or 1100? It turns out it's 11 because you already store in the second register. Okay, so this is not something useful. This is trying to help you understand how it works so you can implement quantum teleportation. Because you need to do the teleportation swapping later. Yeah. Because here I already store 1 in the second register. And here I measure it and store 1 more time in the third register. That's why I have 2, 1. Okay? So think about this is 4 people. Each one is a register. This statement say that, hey, number 2, please measure it and store in your brain. Then he got 1. And then the next one, measure again. Number 3, please measure it, store in your brain. Then he also got 1. That's why you have 2, 1. Okay.
If I did the diagram, it should be the measurement of the qubit number 4 that you store.
No, here is the final outcome, not yet. Okay, I'm talking about D. Okay, and then the last one is E. What happened to E? E say that, okay, do a measurement, but on qubit 0 and store in 3. So this one will got erased to 0 because it is 0, right? Then you get this one. And that's why you get this outcome if you try to do measurement. Over time already, so I will stop here. But think about that next time. I have another 2 examples. Okay.